Good morning, guys. Today we're going to be looking at displacement, velocity, and acceleration. But before we do that, let's take a little peek at other rates of change first, different applications of the derivative. And just remember, what is the derivative? The derivative, in its most simplest form, is basically a slope, okay? We call it a change in y over a change in x, okay? And we kind of build ourselves out of that delta notation a little bit in calculus, and we start to look at it as dy over dx, which basically, what these are called here, this is called differential notation. These are differentials. My smartboard is not working well for me today, and differentials, they mean the same thing as change in y and change in x, except differentials were really more implying very small changes in quantities for these two values, okay? We're not looking for large changes in y over change in x. We're looking for very small changes in y over changes in x so that we can hone in on an instantaneous rate of change in the end, okay? Now, the other thing is, as I'm looking here in differentials, as I'm looking at my notation of my derivative, if I tried to place that into a graph, okay, remember the numerator is going to be my independent. That's going to be my independent variable, and the denominator will always be my dependent. Or excuse me, I got those flip-flopped. I'm sorry. Writing these back because this stupid thing's not working very well. Independent is on the bottom, dependent is on the top, okay? And the way I remember that, independent and the top is going to be dependent. The way I think about that always is if I had a rate of change, or if I have something and I had to graph it, my x and my y, I'm talking about a change in x, change in y, so my numerator is always going to be my y-axis variable. Why do I bring that up? And I bring that up because if we're looking at different things, like here, a change of a quantity with respect to time, okay? Maybe we're thinking about gallons per hour, okay? And if I needed to do that, I could also be looking at cost change with respect to amount of something produced, area change with respect to radius. And as I'm looking at graphs of derivatives and such, like if I looked at this top one, change in quantity with respect to time, if I thought about it as gallons per hour, this would be my gallons axis, this would be my hours axis, so I can look at my change, okay, change, vertical change, horizontal change, top over bottom, rise over run. So this is how we can always bring these in, okay? Now, when I'm looking here too, units on a derivative calculation are dependent on the units of the dependent and independent variables, okay? Well, that's exactly what I was talking about up top. Now, there's lots of different notations that we can be looking here. We can be looking delta y over delta x, dy over dx. Most of these, okay, are the ones we will be using, and those are the differentials notation, okay? And also, like if I looked at a graph of something like this, it tells me a lot about the graph at the same time. Not only if I think of dv dt, let's think of the v, let's say we're talking about change in volume over change in time, which we will sooner or later. We'll be talking about related rates, or change in area with respect to radius, okay? If I'm thinking dv dt, this is my volume axis, okay? And this is going to be my time axis. And my time is always going to probably be in terms of seconds or hours or minutes. It's always going to let me know that. But furthermore, it doesn't just tell me about the graph, how my graph is interpreted. It also tells me volume is a function of time, okay? So my time over here my volume function is written in terms of time, t, so my independent variable would be t, plug in a time for a particular volume, all right? And just take, just a little skim here. Let's take one example. Write an area, write the area of a circle as a function of its circumference. Well, what do we know about a circle? Well, we do know the area in terms of the radius, okay, is pi r squared. But I want to write the area in terms of its circumference, okay? I know area is a function of radius. Well, I also know that my circumference can also be written as a function of radius, correct? Which is 2 pi r. And what I can do is I can utilize both of these variables, okay, or these two equations. Radius is the same in the area as well as the circumference function. And everybody knows circumference equals 2 pi r, okay? Well, that means I can solve for my radius, which would be circumference divided by 2 pi. Well, I can put these two equations together so that I can rewrite my area of a circle. I can take my area equaling pi r squared, and I can write it in terms of circumference because I know circumference is 2 pi r. If I solve my radius in terms of circumference here, well, I know my area will equal pi, and then my radius is circumference divided by 2 pi squared. So I can redefine, I can use these two variables to redefine my function. So my area is going to equal pi times circumference squared over 4 pi squared, which allows me to say area equals, that's going to get rid of that, circumference squared over what? Over 4 pi. Well, just think about this. 4 pi, pi is a constant. Area here is written, my area is written as a function of circumference, and I could say it's 1/4 pi times circumference squared. Now I just rewrote the area of a circle in terms of its circumference, which means if I knew what the circumference of a circle was, okay, I could find the area of the circle. Well, there's lots of different reasons, why we would potentially do this. And if we're looking for here in part B, find the instantaneous rate of change of the area, okay, instantaneous rate of change, what is that? Instantaneous rate of change, that's derivative. Okay, instantaneous rate of change of the area of a circle with respect to their circumference. Well, that means I would have to have a formula where my area is a function of the circumference of a circle, okay? So what does that mean? Well, let's take our area equals 1/4 pi times circumference squared. Well, instantaneous rate of change, okay? If I'm looking for, looking for a rate of change of area with respect to circumference, what I'm really kind of looking for is a change in area over the change in my circumference, and circumference is my dependent variable. So I'm kind of looking for a DADC. What is this? It's a derivative, okay? Instantaneous rate of change, that's really saying find A prime, find the derivative of the area function when your function is defined in terms of circumference, okay? So I can do that. I can come right over here and I could say A prime equals, well, here's a constant of 4 pi times, here's my function, that's going to be a 2c, drop my power 1, it's going to be to the first power. So my area function equals, well, I can see this comes over and that's going to reduce, so I get 1/2 pi times circumference, okay? So what does that give me? Well, that's actually the change in area with respect to circumference, okay? And this could be listed as a prime of c is going to be 1 over 2 pi times circumference. I could call it dA dc, and let's evaluate the rate of change of the area of the circle at when the circumference is pi and 6 pi. Well, what does that do? Well, that's basically just telling me evaluate the rate of change. That's saying take my derivative at pi, and notice it's when my circumference is pi, so 1 over 2 pi times pi. Well, I can see that's over 1, so this is going to be 1/2. Okay? How about a prime of 6 pi? A prime of 6 pi, well, that's going to be my 1 over 2 pi times 6 pi. And if I put this over 1, I can see my pi's cancel, and I can see 2 and 6 reduce, so I get 3, okay? Now, the question is, units are very important for us here, okay? And, I went the wrong way, sorry. Units, this is my area prime at pi. This means my change in area at the particular moment when the circumference is pi is 1/2. Well, it's 1/2 what? Well, think about this, okay? Well, if c is measured in inches, because circumference is a linear unit of measure, and a is measured in inches squared, what would be appropriate units for the change in area over the change in time? Well, change in area, well, it's area, it's going to be inches squared. Change in circumference would be inches, okay? Now, we don't want to reduce our units and call it an inch, because my area is changing, okay, at pi at 1/2 inch. That doesn't make sense, okay? We don't want to reduce it. It's going to be 1/2 inches squared per inch. What does that mean? Well, that means for every 1/2 inches squared, my circumference, or for every, let's see, how am I gonna say that? For every 1 square inch, the circumference is changing 1 inch, is what it really means. 3, okay, my area prime at 6 pi, it's changing at 3 inches squared per inch. So for every 3 square inches change in area, my circumference changed in 1 foot, is basically at that moment in time. Okay, my area changes at different moments in time. These are just a couple things that we're looking at, okay? A couple examples. Mainly what we're looking at today is we're looking at vertical motion, okay? And the objective is given an equation. Ooh, objective, very technical teaching terms here, okay? Given an equation for the displacement or position, okay, displacement is position of a moving object. Find an equation for its velocity and its acceleration. Use these equations to analyze the motion of an object. That's what we're going to learn today, how to do today, okay? And it's important that you understand, suppose that a football, okay, looking at these equations, okay, this is a vertical component only of our position, okay? It's not like when we graph this, and we will graph d of t here in a minute, that is not the path that the football follows. This is just the position of the football at a particular time, and it will follow a parabolic motion. However, the path of the actual punted football will not. When you hit a ball with a baseball or a golf ball, typically what's going to happen is you're going to come up, and then it comes down, and it doesn't really follow a typical parabolic path. What happens if we're finding the actual path of the ball? You did that last year in pre-calc when you did some parametric equations. We're not looking into the parametrics right now. We are just analyzing our displacement function and how it's going to relate into velocity and position, or velocity and into acceleration, okay? So what we're going to do is I'm just going to zippity-doo-dah here to my next slide, and we're going to go into our calculator here, and we're going to find the displacement, the position off the ground at a particular time. Now, remember, this, when t equals 0, this is finding the position of the ball at time 0. Well, that's pretty easy. That's 3, okay? 3 what? 3 feet. 3 feet above the ground. Well, how about my position at 1? Well, that's, again, not too bad. I can plug a 1 in. Here's my position 2 seconds into it, okay? So we can do this in our calculator. We'll grab our little calculator. We're going to go graph our displacement function. We're going to hit enter. We get a really crazy, wonky looking quadratic, and get down there. And we really want to be able to look at our graphs, so we're going to change our windows, and I'm going to go from like -1 to 3, 1 on each scale, and I'm going to go from about -5 to 30. It's not a very good punt. And I'm going to put that at about 5. So here, this is giving me, now you get this out of the way. Notice this is not the path that the ball traveled. This is just giving me the height of the ball at a particular time. And as I plot these ordered pairs, okay, as the time goes, the time is going to maximize the ball, but it's not showing the actual path the ball traveled. It's kind of, that's not the end of the world. So let's go find these. We can find these by saying trace the graph. And if I needed to know the position, 1 second in there, well, it's 24. And if I needed to know my position at 2 seconds into it, it's going to give me this 13. Whoa, come on, baby. Oh, and I'll have my 0 on there too, just to show that. I'm going to get those out of there, squirrel these little guys here. So bottom line, I could just use my calculator. My trace function is all. And what I'm going to do is I'm going to come back in here and say my position, my displacement 1 second in is 24 feet. The ball's 24 feet high. Position at time 2, it's 13 feet high. Okay, remember, these are the height off the ground. Okay, and we're going to take that a step further. Okay, there's zero calculus involved here. We have done nothing. This is all pre-calc, finding the position. Well, here's my time, my displacement or position of the ball at any time t. All we're doing is plugging 0, 1, and 2 into the displacement. D is in feet, t is in seconds. When does the ball hit the ground? Well, if I need to know when the ball hits the ground, I need to know when is my position function equal to 0, right? So what I need to do is I need to take my -16 t squared plus 37 t plus 3. Well, we're going to say, when are you 0? Well, the beautiful thing in this class is, typically if they're really ugly, this won't factor. We can use our calculator, and we can use our calculator to find that in 2 different ways here. So I can actually come back to my graph, and I can say menu, analyze, and find my 0, and go left bound, right bound, and say, oh, it's at 2.391 seconds is when it hits the ground. So this ball, when he punted it, was in the air for 2.391 seconds. Really crappy punt. Or if you do not know how to use a solver yet, I know I've showed it once, but I'm going to show again. Open up a calculator page, and this is really nice. And what I can do is, rather than having to graph a function, I can say menu, algebra, solve, and I can type in my function of -16. And if I didn't want to change it, now before I go further, notice over here, I put this in terms of x. Anything we graph in this calculator has to be x and y, right? So I had to change that. When I'm using the solver, I can use x or I can use t, and here's why. So if I typed it in, 16t squared plus 37t plus 3, we want to know when does this equal 0. Most people hit enter here, and they're like, ooh, too few arguments. Well, that's because you didn't tell the calculator what variable you wanted to solve for, okay? It's not looking at t as a variable. So as I do this, I got to come inside and I got to give it a comma, please solve for t. And what it does, ooh, looks like the quadratic formula. That meant it didn't factor. So if you don't want the exact values, bring that bugger down and then give it the control approximate, and it'll give me the decimals. Well, this negative 0.078, we don't have negative time, that's why we don't utilize that, or it's t equals 2.391 seconds. So I can use that wonderful little solver to find my zeros. And we haven't used any calculus, by the way. So I can come on here and I can say, oh, when t equals 2.391 seconds, and remember, in calculus, 3 decimal places is exact, okay? So that's when the ball hits it, 2.391 seconds after the punt, okay? Well, let's take a little sketch of this curve. So we know this is going to be time, and this is in seconds because it's a position. This is going to be my vertical and position, and it's in feet. So if I had to sketch this, you know, I just say maybe 1, 2, 3, and I know 0, 3 is my initial height off the ground. When I kick the ball, I know at 1 second up here, I'm at 24, or crap, this doesn't work worth a word, 124, and I know 2 seconds into it, I'm at like 13 to 13, I'll try, crap, still didn't work. And put my 1, 3 there. And then I also know basically where was I? 2.391 seconds, right about in, I don't know, somewhere in there. So I can see kind of a skanky little graph that I made there. But bottom line, here are the position points that we found with it, okay? Find the average rate of change, okay, over the interval of time from t equals 1 to t equals 2 seconds. And in the end, units are huge for us here, okay? Average rate of change, the AROC. So basically, this problem is saying, find the AROC on the interval from 1 to 2. And remember, we're building today from 1 to 2. And we know how to do that because the AROC, in the end, my average rate of change is going to be change in position over change in time, right? So that's AROC. So that's going to be my displacement at time 2 minus displacement at time 1 over 2 minus 1. Well, we have these values right above there. So where are we at? We're at 13 minus 24 over 1, which actually equals negative 11. Negative 11 what? Okay, units are a huge deal. Okay, remember, displacement, change in displacement, change in time. My displacement is given to me in feet. My time is given to me in seconds. So that would be negative 11 feet per second. And what is that? Negative 11 feet per second? That would be my velocity. That would be my average velocity over the interval from 1 to 2. It is actually taking those 2 points and finding the slope of that line. Right there is exactly what it's doing, okay? That's my average velocity. It's the slope of that pink secant line. Well, Find the instantaneous rate of change at t equals 1. We've done this, okay? The way we did this is we got really crafty for a while and we said, oh, we're going to find the AROC from maybe 1 to 1.0001, and that approximated my IROC at x equals 1. That's what we did, and we knew how to do that, didn't we? So that's my displacement at 1.0001 minus my displacement at 1.0001 minus 1. And we would always come to our little calculator here, and notice I have my displacement function graphed in my F1, okay? So when I'm here, I can grab my fancy little fraction, and I can tell my calculator, please go find function 1 and evaluate it at 1.0001 minus that same F1 function at 1, and then take my 1.0001 minus 1, and I didn't want that. I got to take myself out of exact mode and go to approximate. And am I really ready to approximate this yet? Remember, we weren't always ready, and what we typically did in this scenario is we came back in and we added a 0, and we kept getting closer and closer to 1. Okay, and we could see if we rounded off to 3 now, we do see that we could say that we are at, okay, first and foremost, we approximated this at 4.9984, but then as we let our change in time get closer and closer, and we kept going closer to 0, we found out that a good estimate was 5 feet per second. Okay, well, what is that? What is the instantaneous rate of change at t equals 1? Well, isn't that really the derivative of displacement, the first derivative at 1 second? Okay, what about the instantaneous rate of change at 0, 2, and 3? Well, all of those are obviously easier to find, okay? And they're easier to find if we actually found the derivative, okay? Well, what is the derivative? Well, let's pull this down a second. What are my units? So we're going to come back here, and we're going to look back all the way back to our original function, where d of t equaled negative 16t squared plus 37t plus 3. So if I took the derivative of my position, I got negative 32t plus 37, right? And as I'm cruising along here, what did I really do here? Well, it's really kind of nifty. In the end, we're using properties, but remember, this is coming from the limit as h approaches 0 of d of t plus h, okay, my time, plus h, where h goes to 0, minus d of t all over h, okay? And in the end, what was that? That's my change in position over my change in time. My position was given to me in feet, my time in seconds, so I get feet per second. This derivative right here, which is also right here, is given to me in feet per second. That is my velocity. Oop, can't spell velocity. That's my velocity function. Okay, feet per second. That's my velocity. Change in distance, change in time. Just like if you're going to grandma's house. What was your velocity? Well, if you went 50 miles an hour for an hour, what was your average velocity or your change in distance, change in time? You drove 100 miles at 50 miles an hour, average velocity. You can get it, okay? You can just go through. and find all that good stuff. So what we just found here, hopefully I'm not scrambling your brain, velocity the velocity function of a horizontal movement or horizontal position, velocity function is the first derivative of position, not just because velocity is the first derivative of position, because of units. It just makes sense, okay? Change in distance, change in time. That's velocity, feet per second. It gives me, number one, a direction I'm traveling, and how quickly, it's telling me how quickly I'm traveling. It's giving me my speed, but am I going forward or backwards? It's giving me both of those at the same time. So that means the derivative of position is my velocity function, okay? So what does that mean for me? Well, that means d prime of 0, the derivative at 0, is the same as my velocity at 0, which is 37 feet per second, okay? Remember, up here, we had our d prime of t, and we found that to be 32t plus 37, and if I plug the 0 in there, that's what I got. The derivative, or what's my velocity at 1 second, my velocity at 1 second, and all I keep doing is, so you understand, derivative position, first derivative of position is velocity, and if I plug that into my velocity function, that's a negative 32. What do I get? This is 5 feet per second. How about my velocity at 2 seconds? Well, remember, that is the derivative of position at 2, and all I got to do is squirrel my seconds into that, and what do I get? Negative 64 plus 37, negative 27 feet per second, okay? Well, what if I wanted to take it a step further, okay? What if they asked me in an application like this, what was the velocity of the ball when it impacted the ground? Well, that means I need to know the derivative when it hit the ground, and we knew it hit the ground at 2.391 seconds, so that's my velocity at 2.391 seconds, and that happened to be negative 39.509 feet per second. Okay, it's giving me my velocity at impact when the ball hit the ground as I'm cruising along through. Okay, so let's take this a little further. So if the derivative of position equaled velocity, what does the derivative of velocity equal? Well, let's think about this here a second, okay? This is going to be my rate of change of distance, okay? Rate of change of distance, okay? And what do I know about that? I know my derivative is going to be change in distance, change in time, okay? I know my change in distance is represented as feet, time is represented as seconds, okay? So that is my rate of change of distance. Rate of change of distance is velocity, which we call in calculus v of t function. It's a physical quantity of the derivative of displacement is what velocity is. It's the physical quantity of d prime of t, okay? Well, so what does that make v of t? Well, that means v of t, well, that is taking what? Rate of change of velocity. Okay, and if I think back, v prime of t, well, that's taking my change in velocity over my change in time. And here's where it really kind of comes together, because what are my units of measure? What are my units on change in velocity? Well, my velocity is feet per second. So I get feet per second. Time is still in seconds. So I get feet per second per second. Ooh, and the rate of change of velocity, you know what that gives? That gives us acceleration. And in calculus, we call acceleration a of t, okay? And all these connections that we're thinking a lot here is a of t, we can call that a few different things, okay? We can call that v prime of t. The derivative of velocity is acceleration. And the derivative of velocity, that would be the second derivative of position. So I can get all these cruising all the way through here. So as I'm moving along and I'm finding all these equations, okay, units, people screw up a lot on velocity because of what's this, feet per second per second. Well, all I really have here is a complex fraction. So I really have feet per second times the reciprocal multiplying by the reciprocal of the bottom, 1 over seconds. Well, that gives us feet per second squared. So acceleration has feet per second squared as units on it, okay? So what do we got going on here? So what we got going on here is our displacement function originally given to us was negative 16 t squared plus 37t plus 3, okay? And if I took you all the way back into Algebra 1 when you looked at these functions, okay, hopefully you remember that was always your initial position. 3, the constant was your initial position because that was at time 0. And the other place that we come through here is we always had to plug in our initial velocity too, our v sub 0 of t, as we called it. Well, we can figure all this stuff out. That's my initial velocity at 37, because when I come back here and I find what v of t is, well, v of t, remember, that's the first derivative of position, which is going to be negative 32t plus 37. 37 is the initial velocity because v of 0, guess what it equals? 37, but I can catch that all the way back in the beginning. Okay, and what's my acceleration? Well, remember, a of t comes from v prime of t. V prime of t came from d double prime of t. So it's the second derivative of position. That gave me negative 32. And what the heck is negative 32? And I guess I should put on here feet per second squared. These are feet per second, and position is given to me in feet. So I got to keep my units. I got to keep my units in mind all the time with which function I'm working with. Negative 32 feet per second. Well, for all of you guys in physics, yeah, that's the acceleration due to gravity. Okay, we're almost done. Hopefully you're not too confused and scrambled. If d of t is the displacement of a moving object from a fixed plane and t is time, well then velocity v of t equals d prime of t. Okay, well, yeah, we knew that. That's what we were talking about here. Okay, well, what does that really mean? Well, notation is what we're really kind of focusing on here. And what that really means is there's another way to say this. I could say it's the derivative in terms of time of my displacement function. And the way I'm writing it here is, please remember, that is a function of t. Okay? So when I'm doing this, v of t is d prime of t, which also could be called the derivative in terms of t of d, which in differentials we call dd dt. The derivative of displacement with respect to the derivative of time, dd dt, okay? Which we can call v of t, okay? And they just keep cruising along. Acceleration. Well, whoa, a little nutty there. So acceleration, well, acceleration is v prime of t, okay? And let's just remember what v prime of t is. Well, that's the derivative in terms of t of v is what that means, okay? V right there, that's in terms of time. Well, that equals dv dt. And in the application I'm talking about right now, this wouldn't be implied volume, derivative, velocity, derivative of time. So you always have to keep track of the application in which you're using. Now, if I really needed to figure out what second derivative, because second derivative notation can come in a few different ways, and what this really is, it's d squared d of dt squared. And the best explanation I have for you is, I'm not even going to talk about recall from physics, but if I come down here, okay, what I want to do is I'm taking dd, or d over dt of d. Well, that's my first derivative, right? And I want the derivative of that. Okay? So as I come across here, this is going to give me d dt, basically times dd dt. And remember, this stands for derivative. So I'm kind of thinking d squared derivative d time squared, and there's really a little parenthesis kind of around that. So I kind of look at the second derivative is sliding these two across, thinking of a d squared dt squared of d, and then that's why I go d squared d dt squared is kind of how I look at that. The only thing recall from physics, those of you that are in physics, we can make the connections here a little bit. Position in physics, what do you guys call it? 1/2, I think, g, acceleration due to gravity times t squared plus initial velocity times t plus original displacement. And then your v of t is found to be what? Well, that's really d prime of t, okay? But you guys look at it as acceleration due to gravity times time plus initial velocity. Well, check it out. If I took the derivative of this, 2 times the half, gets rid of that, doesn't it? And I'm left with g times t. G is a constant. G is an acceleration due to gravity. And our acceleration, well, in calculus, we call that v prime of t. Didn't really need this guy right there. And the other thing we can call it is we can call it the second derivative of displacement. What did you guys call it, or what do you call it in physics? Acceleration? Oh, g, acceleration due to gravity, negative 32 feet per second. Negative 9.8 meters per second, I think it is, okay? So bottom line, what did we just learn through all of this? Hopefully you're understanding what we just learned. That, let me come back to it, okay? Can you find an equation for velocity and acceleration given displacement? Coming all the way back to my, given an equation for displacement of a moving object, can you find an equation for velocity, which is first derivative? Can you find an equation for acceleration? That would be second derivative. and use these equations to analyze the motion of the object. Well, feet per second per second, finds out how fast it's going, which direction, blah, 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 all that. So that's what you're going after today, and we will pick up on this packet, which is the moon problem, I think day 2 tomorrow. But I'm done for today. Have a good afternoon or morning, wherever you're at.